Okay, welcome once again to your study part. The subject is physics, and the teacher remains Mr. Oluwafemi. It's nice having you on board once again. Today, we're going to be looking at certain review questions from the subject of physics, cutting across the different branches of physics: mechanics, heat and temperature, waves, light and sound waves, not forgetting electricity and magnetism, and also dwelling on basic electronics and atomic and nuclear physics. So we want to look at some question review on different parts, knowing fully well that your UTME examination has finally kicked off. And the best we can do is what? Touch on every question which you need to get yourself familiarized on. Let's get started quickly. Question one today will be taken from your SS1 scheme of work, talking about scalars and vectors. And the question is this: which of the following quantities is a scalar? Which of the following quantity is a scalar? So question one, scalar quantity. A, is it velocity? B, is it acceleration? C, is it displacement? And D, is it temperature? We have identified that scalar quantities are quantities that have magnitude. You can measure the size, you can't measure the direction in which they are taking effect. But vector quantities are quantities that have both magnitude and direction. You have a velocity is a what? Vector quantity. You can talk about running 5 kilometers per hour in towards the church or towards the school. Now you have a direction where you're going. Um, Acceleration, also you are accelerating at 5 meters per second square towards the venue. So it means that what? There's a direction to where you are going. Displacement means you are having a distance covered with respect to a specific direction. Oh, I am walking at a pace of 5 meters per second upstairs. So going upstairs, you have a direction where you are headed. So magnitude, direction, vector quantities. The only one which is the odd one out, which is going to be the answer, will certainly be what? Temperature. Why? It measures the magnitude of increase in the heat quantity of your body. It never talks about the direction of motion. Remember, the body is stationary and you're having whatever metabolic reaction taking place within the body or on the body. So note that temperature is a scalar quantity in this instance. Number two, question of the day. We are told that what? The primary purpose of your depletion region. Number two, purpose of depletion region, or we call it depletion layer in PN junction diode. We've said that your PN junction diode is the positive negative type of diode, where you have the P and the N joining together. So when you're having your PN junction diode, there's always a middle gap in between, which we call the point of fusion, which we refer to as the depletion layer. So this is where we are making reference to as the depletion layer. So P and the N, you have it connected to your terminal. And please have it at the back of your mind that this kind of connection will tend towards expand the depletion layer, because what type of bias is this? We refer to this as a backward bias. This is not a forward bias, a backward bias in the sense that what? Imagine this being positive, this being negative. You are going to have attraction between the positive and the negative. So as such, you have the carriers flowing away towards this side. You have that what? Your N-type semiconductor, you will have carriers moving towards this side. As such, the depletion layer is going to expand in this regard. For forward bias, we have that there will be a change in the terminal of your battery source. But all that is a bit limited to the structure of the question. The question here is that what's the purpose of the depletion layer? Is it to increase the diode current? Could it be that it is to reduce the diode saturation current? Is it to increase the diode current? Is it to reduce it? Is it to create a potential barrier? Or is it to enhance the diode switching speed? All these might not be popular words for you, but let's break it down in simple English. You should understand that what they are not asking for function of the diode. When they are asking for the purpose of a diode, then you are directing your answer towards current. You are making reference towards current as your answer. But the moment they are asking for the purpose of the depletion what layer, it's the depletion layer you are asked here now. And what we are going to say is that what it's going to create a potential barrier. It helps to create a potential barrier. The purpose is to create a potential barrier. To charge carriers. In a diode. It tends to create what? It tends to create a barrier because you won't have electrons being able to flow easily from one part to the other along the diode. It tends to create what? A potential barrier when you have majority carriers moving across to each other junction, positive to negative or negative to positive. That being said, we move quickly to question 3. Remember, we want to look at as many questions as possible. The next one is talking about atomic physics. What do we have under atomic physics, or what can we say about atomic physics? We say that the implication of Heisenberg's uncertainty principle with regards to particle position and with regards to what? Momentum. What can you say about it? We identify that Heisenberg's uncertainty principle stipulates that you cannot determine the position and the momentum of a body at the same time. Heisenberg's uncertainty principle, that's question 3, states Heisenberg's uncertainty principle. So, you have that what? When you have that, Heisenberg's uncertainty principle is indicating that you cannot measure both the position and the momentum of a body at the same time, simultaneously. Then a question can be drawn around it, saying that the implication of Heisenberg's uncertainty principle on the position and the momentum, could it be that both position and momentum can be precisely known? Can you know the exact position and momentum of a body at the same time? No, because Heisenberg's uncertainty principle says you cannot do that. Is it that B, you have a more precise instance whereby if you know the position of a body, you can't easily determine the position of the momentum at the same time? Yes, that's making sense. C is saying that if you are familiar with the position, if the momentum of a body, you can precisely know more about the position. That's unlikely. And D is saying the position and the momentum are unrelated. That's never true. Heisenberg's uncertainty principle is telling us that Heisenberg's uncertainty principle is telling us that what? Both momentum and position cannot, note, cannot be determined. Cannot be determined simultaneously. Cannot be determined together simultaneously. So this is what it's saying. You can't measure it. Okay, it's practical. Imagine me being here. It's easy for me to say that the distance between myself as a person And this line here now can be measured easily by what? Making use of a meter rule, for example. I can determine my position away from this particular line. But the moment I'm moving away while in motion, momentum considers the change in the mass, the change in momentum will work with what? Mass and change in velocity. The mass of the body and change in velocity. So the moment I'm moving away from my original position, you cannot measure exactly my position again. So you have to measure one. Either you're measuring my position while I am not moving, or you are measuring my momentum while I am moving. So Eisenberg is saying you cannot determine together the position and the momentum. So we have that the more precisely you know the position of the body, the less precisely you are going to figure out the momentum of the body. So that's what the answer is. So if you know how to state Eisenberg uncertainty principle, you are good with answering that. The next question will be around wave. Let's see something on wave. We have that what is the phenomenon where a particle passes through a potential energy barrier, even if it does not have enough energy to classically overcome the barrier. I come again. What is the phenomenon where a particle passes through a potential energy barrier, even if it does not have enough energy to classically overcome the barrier? So whenever you're having that a particle is actually passing through a potential barrier, when it does not necessarily possess the energy to overcome a barrier, then would you talk in terms of reflection, reflection? Will you talk in terms of refraction? Will you talk in terms of diffraction? Or will you talk in terms of tunneling? So, which of these would you specifically make reference to in terms of particles passing through potential energy barriers? Now, reflection, you know that what? Reflection is attained when light strikes a reflecting surface, and tends to what? Deviate at an angle away from such surface. So you have light striking a surface and bouncing back as a result. So reflection certainly has nothing to do with what? Overcoming an energy barrier. You talk in terms of diffraction. Diffraction is making reference to a body, and you have a wave, or you have that what? Generally a wave or a particle trying to what? Bend around obstacles while moving. Water trying to what? Dodge and pass around obstacles. Your radio wave or Wi-Fi, for example, in a room, trying to what? Pass through window openings for signals to be what? Received outside of the room. So you are in a room, you have your hotspot, you have your Wi-Fi turned on, and the window is open. You have that the potential signal becomes strong outside to the person standing outside, because there are openings for which the frequency of the Wi-Fi can pass through. But the moment you're having your windows locked, your doors closed, then the signal strength tends to what? Reduce. So in this case, when you have that wave of particles passing or bending around obstacles, then you're talking about diffraction. Refraction is making reference to a situation whereby wave tends to what? Light wave, for example, tends to pass through what? Mediums of differing what? Density. You have light, for example, traveling from a less dense medium to a denser medium. Light passing from a less dense medium to a denser medium. So once you have a change in what? Medium, there's going to be change in velocity. Note that when you have change in medium, there's certainly going to be change in what? Velocity. As such, this cannot be the answer. We're making reference to energy barrier. Tunneling certainly is going to be the answer. So what are you going to do next time? For example, you are not familiar with the concept of a word, try to do elimination method. Look at the ones you know you're familiar with and try to eliminate the ones you know that cannot be the potential answer. So in this case, tunneling certainly is going to be a situation whereby a particle is actually what? Passing through a potential energy barrier despite not having the what? Potential to overcome such barrier. We move on to the next one. So this is definition of the above. So that's what we looked at for number 4. For number 5, if you're asked, what's the unit of force? Certainly under fundamental and derived quantities. What's the unit of force? This should be a walkover for you if you see this question. Certainly, it's not joules, it's not kilometer, it's not meter per second. It's certainly what? Newton, the unit of force. Number 6. So you can always have questions that are easy. That's why I keep emphasizing. Why not go for the non-calculation question first? Try to look at questions for which you can just what? Wrap your heads around within the space of 20 seconds to 30 seconds, such that you can have enough time to now look at calculation questions. You can determine exactly and precisely how the ton of questions can be involving calculation questions. Let's look at the next one. If you're asked that, what is pressure? Imagine a question as that. Pressure. We've identified that pressure can actually be defined under 2 aspects. It's either you are talking about pressure in solid or pressure in liquid. So depending on what the options are presenting to you in your UTME examination, if they're making reference to force, then you know that pressure in solid is what they're making reference to. So what are the 2 definitions for pressure? We say that pressure is force per unit area. That's where we have that P is equal to F over A, or we're making reference to pressure as the product of density, depth, and acceleration due to gravity. So we have P as being equal to rho G H. I come again. Pressure definition can always be in 2 forms. If you are asked in terms of force, then you know you are dealing with force over area, or you are dealing with what? Pressure in liquid. Then you'll be dealing with what? The density, the depth, and the acceleration due to gravity, rho G H. So in the question, pressure is simply defined as force per unit area, as identified for what? Solid pressure. The next question now. Under motion, let's look at a question under motion. If you're asked the question as direct as, when is a body said to be in motion? When do you say a body is in motion? At which instance is a body in motion? Is it A, when the body has constant velocity? B, is it when the body remains in the same position? C, is it when you have change in position with time? Or D, is it when a body is at rest? When do you say a body is in motion? Note, you'd always make reference to a body in motion once you're having a change in position with respect to time. You have that a body is in motion once you're having what? A change in position with respect to time. Change in position with respect to time. So I'm here and my position is changing as the time is counting. Note, as the time is counting, my position is changing. This you say that what? I am in motion. What? My position is changing as the time is ticking by. Then you have that what? The body is what? In motion. So note that change in position with respect to time. So, and that leaves us with the fact that is related to what? Definition of motion. Go back to your what? SS1. This question is centered on what is the definition of motion? Define motion. That's what we have here. Your definition of motion is all they're asking you for here. So if you can define motion, can you go taking it a step further? What are the types of motion? We say that the types of motion would include your random motion. Don't forget, it would include your rotational motion. It would include your translational motion. And you are going to have your, we have our random, we have our rotational, we have our translational, and we have the oscillatory motion. So these are the 4 types of motion. We know that we can take it a step further in the A-level classes. You see them mention relative motion, meaning a body moving relative to the motion of another body. So a mother backing a baby, you have that the baby is moving subject to the motion of the mother. When you have that a person inside an aeroplane moving backwards to the direction of the aeroplane, you have that what? It's a relative motion because the person is moving towards the back side of the aeroplane is moving forward. So you're going to have a form of relative motion that way. So you have relative motion. Bear that in mind. Now, having identified the question under motion, we want to take something very easy and very cheap, which you can actually place your mind on. And what's that? From secondary school, the junior school, we were taught about energy. And this question here is relating to energy. Can you state the law of conservation of energy in terms of how your Jamb examination body wants of you? Law of conservation of energy. Law of conservation of energy. What can you say about it? Is it that energy can be created and energy can be destroyed? Or you can say that energy can change from one form to another, or you can say that the total energy in an isolated system is actually constant, or you can say that perhaps everything I'm saying so far is correct. Talking about energy can actually be created and energy can be destroyed, or you can say that energy can change from one form to another, or you can say that total energy in an isolated system remains constant. The correct answer would be your energy in a closed system being what? Constant. Remember that the popular one which we are taught is that what? Energy can neither, not the word, neither be created nor destroyed. Energy can neither be created nor destroyed. You can't create energy and you can't destroy energy. So as such, you won't have energy being created and energy being destroyed. Yes, energy can change from one form to another, but the problem is that what? You can't negate this part here. You can't isolate the fact that energy cannot be created and energy cannot be destroyed. So before you continue saying that energy can change from one form to another, note this part. So this part, neither part of this law can be stated separate. They have to come together. When you are talking about the creation and destruction of energy, you should also tell us what happens. There can always be a transformation from one form to another. And that brings to bear the fact that what? It's not only this that we have as the conservation of energy law. You have another law that stipulates that the total energy in an isolated system remains constant. The total energy in an isolated system remains constant. This you have as the second form of presenting your law of conservation of energy. So put that in mind. And remember that what? We have this also similar to the law of conservation of momentum, where you are making reference to the fact that what the momentum which you are going to have for the change in momentum which you are going to have for an isolated system is always constant, or the momentum before collision and the momentum after collision remains the same. So this aspect remains the second way of presenting law of conservation of energy. Energy can neither be created nor destroyed, but you can change them from one form to another. Then you can say that the total energy in an isolated system remains what? Constant. We push on. Question 9. When you are asked that the acceleration due to gravity on the surface of the earth, what can you say about it? Acceleration on the surface of the earth. You have that what? For the earth, acceleration due to gravity is approximately 10. Note the word approximately 10. But it ranges from what? (9.8 meters per second) and approximately what? 10 meters per second. But it's not for you to just know this only. What if the question is directing you towards moon, the moon? What is the acceleration due to gravity on the moon? What is the acceleration due to gravity on the moon? So we said that what? G on the moon is equal to 1/6 of G on the earth. Note, G on the moon is 1/6 of G on the earth. And that's why when you divide 1.8, 9.8 rather, divided by 6, you have a value around, so let's use 10. You have a value around 1.67, which is the general case scenario you see in most books. 9.8, approximately 10. You can easily say that what? The acceleration due to gravity on the moon is 1/6. It is not 0. Note that. The acceleration due to gravity on the moon is not 0. That's why you can always see people upping on the moon. You see them upping from one position to another. It's simply because there is still what? Gravity, only that it is very small. Bear that in mind. 1/6 of that of the earth. We look at the next question with regards to wave. What can you say about wave? And that boils down to the definition of wave. Remember, UTME examination is very, very easy. But bulk of it is centered on how best you can remember or you can relate with certain simple questions. The clear understanding you have about certain physics concepts. So in this case here now, If they're asking you, can you define wave? Then if you answer is yes, you should be able to answer the next question. Because the question is asking that which of the following statements is actually true about wave? Can you easily say that wave cannot transfer energy? Is that a correct statement about wave? You agree with me that that is never true, because wave involves the transfer of energy. You know that you cannot remove that from the definition. Wave is the transfer of what? Energy. So a statement saying that wave cannot transfer energy is definitely wrong. B is saying this: wave requires a medium to transfer, to travel. That is making sense to some extent, because it's subject to the type of wave. C is saying that all waves are transverse. Certainly not. We have different types of waves, and we cannot say all waves are transverse. That is a potentially incorrect statement. When you're saying wave cannot transfer energy, it's potentially wrong. Then the next one is saying that waves can be seen when they pass. Waves can be seen when they pass. Not all waves can be seen. You have that what? Not all waves can be seen. So here a question saying that an answer or a statement being made and telling you that what? All waves can be seen when they pass. That's not correct. Not all waves can be seen. You have that what? Radio waves cannot be seen. You cannot see radio waves. So not all waves can be seen. So in this case here now, what are the key highlights of waves which you want to get yourself familiar with? Number one, based on the definition, you can say that waves transfer energy. Waves transfer energy. You can say that what? Waves can be transverse or longitudinal. Waves can be transverse or longitudinal. That will be the correct statement. Waves can be transverse or longitudinal. Another thing you can say is that what? Some waves require material medium, while some do not. Some waves require material medium, while some do not. Some waves require material medium, while some do not. So these form the basis of picking answers. You want to understand that a question under wave being asked the definition or the classes of wave, and you can what? Easily answer. Now, not this part, requiring material medium or not requiring material medium. I'm sure you know that that's either making reference to what? Your mechanical wave or electromagnetic waves. When waves require material medium, then we are making emphasis on mechanical waves. When waves do not require material medium, we are talking about electromagnetic waves. As such, this part here is talking about electromagnetic and what? Mechanical waves. Here, talking about transverse and longitudinal, then you are making reference to direction of propagation with respect to direction of vibration of the wave. So, transverse and longitudinal. Do you have that waves are traveling parallel to the direction of propagation, to the direction of vibration, or you're having that waves are traveling perpendicular subject to the vibration of such wave? We push forward. Now, talking about electricity, we've not looked at much questions on electricity. So if we're diving into the aspect of electricity, and you're asked that what is the purpose of a fuse in an electric circuit? What can you say is the purpose of a fuse? You might have heard of fuse before. I wish we have one. Yes, we do. And this is it in your homes. You'll see that what your chargers, your laptop chargers, would always come with something unique. When you observe closely, you get to see that what this part is detachable. We can detach this. I don't have something small. Okay, I wish there was something I could use. But anyways, now when you observe closely, you see that what when you look at your charger, your laptop charger, for example, there's something for which we can disconnect and remove here. When you observe the three terminals here, the earth, the live, and the neutral, when you observe them, in the middle, there's actually something placed inside here. That's what the fuse is. And in this case, we call it a cartridge fuse. A cartridge fuse. You can easily remove it and fix another one back. What is the purpose of this fuse in an electric circuit whenever current is being transferred in the circuit? Is it to do the following? Let me read the options which we have and let's see which one is going to be the best of answers. We have that. Could it be that the fuse which you're having in your laptop charger is actually there to increase the voltage? Do you have that what? The purpose of the fuse is to increase the voltage. Or could it be that the purpose of the fuse is to reduce the resistance? Could it be that the purpose of the fuse is actually to protect against overcurrent? Or could it be that the purpose is to filter out AC current? So, certainly funny options as the case is. But let's break it down. You don't have fuse increasing voltage. Note that. You don't have fuse increasing voltage. Let me tell you what you use to increase voltage. Anytime you're having that, you want to raise voltage up a certain value, what you use is a transformer. I come again. The moment you want to increase voltage, what you use is a transformer. To be specific, you use a step-up transformer. A step-up transformer. Whenever you want to increase your voltage, step-up transformer. Whenever you want to decrease your voltage, step-down transformer. So it's that clear on the part of voltage. Here, when you say you increase, you reduce resistance. When you reduce resistance, guess what you are doing? You are increasing current. If you remember, we said V is equal to IR. When I want to find the relationship between I and R, I'll divide both sides by R, such that I can say that I is equal to V over R. So, if you have that what? R is being reduced, I will be what? Increasing. They are inversely proportional to each other. So when you are reducing your resistance, you are increasing the current. A fuse is not used to increase the current entering your charger. What your fuse does is to what? Protect your charger against what? High current, excess current. So once the current exceeds the fuse rating, once the current coming from the mains exceed the what? The fuse rating, it is going to what? Cut. And it will not allow that excess current to flow inside your what? Device. That's the purpose of your fuse. It cuts excess current and it prevents what? Excess current from passing from the mains, which is your NEPA, your generator, whichever one, your main supply, AC supply, into your device. But you trust us, in this part of the world, Nigeria, you have some people telling you, oh, don't bother, just connect a tiny wire across that part. Instead of putting that cartridge into what? That terminal. You can always easily just use a tiny wire. What you are trying to do is a fuse bypass. It's no problem. You will have current flowing and your charger starts working back. But the day you have high current being supplied, your system suffers for it. And guess what? Systems and laptops of today, flat and portable laptops of today, you have that what? Once excess current is supplied, the first thing that gets damaged is the motherboard. Trust me on that. The motherboard is what suffers for it. So it means potentially you are buying a new laptop. So please avoid that error when some engineers in quotes tell you it does not mean. Fields serve their purpose. So we said that fields tend to protect against excessive current. That's the job of your fuse. Quickly pushing on. If you are asked that what is the principle behind operation of a transformer? So I want to dwell on two questions under electricity at the same time. I talked about transformer not quite long and telling you indirectly the types of transformer, two types of transformer, step up or step down. So you're now asked, what is the principle behind a transformer? I'm sure you might have seen this in your textbooks. You have this, and you have a loop. One is smaller than the other. Once you're having that, this end is called the primary winding. This part is called the secondary winding. When the primary side is less than the secondary side, you say this is a step-up transformer. From the primary, you are increasing to the output side. The primary is the input side, the secondary is the output side. So this is a step-up transformer. So in this case here now, whether a step-up transformer or whether a step-down transformer, whereby this side will be more than this side, this is called the iron core. They operate on a specific principle, and the principle transformer operates on the principle of electromagnetic induction. Electromagnetic induction. Electromagnetic induction. And take your mind back to the man that gave us that, Faraday. Faraday's law of electromagnetic induction, which stipulates that the induced EMF is always proportional to the change in magnetic flux linkage with respect to what? Time. Making reference to time there. That the rate of change of what? Magnetic flux linkage is directly proportional to what? The induced EMF. Mathematically, we find out that what? E representing EMF. E induced is always directly proportional to what? Change in N representing the number of turns, then change in what? Magnetic flux linkage, phi over the T. For those of you that have not written your UTME examination, you can always look all these things up. That's the purpose for which we are actually what? Enlightening you. Check these out. Try to check this out. 2 to 3 questions more before we call it a day. The next one is this. When you have opposition to the flow of current, what do you call opposition to the flow of current? Certainly not a big deal. It's not called inductance, neither is it called capacitance, neither is it called conductance. What you have is resistance. Opposition to the flow of current is called resistance. So that's why you see that under the resistance question, I wouldn't know which one we dealt with. You have that when I was talking about fuse, it does, when you have a decrease in resistance, it means you have increase in current. So, okay, I wrote V equals to IR. There, I was making reference to V over R equals to I. So you have that what? Opposite of current is resistance. Bear that in mind. Then you have the next one. Asking us that what? When you have that wave change direction when it passes from one medium to another, take your mind back to this guy. Where is it again? Here. I talked about it among these guys. Whenever wave is changing direction, the velocity changes. The moment is moving from one medium to another. The best answer is what? Refraction. That's why I said definition of the phenomenals above. So refraction, you always have that medium, one medium to another. is always involved. And last but not the least, you're asked that what type of energy will you say is present when you are stretching, when you have a stretched or compressed string? Note, what energy is stored in a stretched or compressed string? Note the word, the stretched string or a compressed string. What form of energy do you have in either case? Could it be kinetic energy or potential energy or thermal energy or electrical energy? You can always knock off the wrong answers. Electrical energy has nothing to do in the business of things. Potential heat energy, which is thermal energy, has nothing to do. It's between kinetic and potential. And we said that kinetic energy is energy in motion. You have a body in motion, but we have the potential energy is always energy at rest. When you compress something, it is not moving, it's compressed, it's at rest. So that's potential energy. When I stretch a rubber band, for example, you have that it is stretched in this instance. As such, it's not moving. You are stretching it. So it's attaining the highest point. So you have that what? That potential energy. And with that, I would say we have marked the end of today's class. I'm sure we've been able to touch on certain questions that you're familiar with, but you don't have clear, concise ideas about. We've been able to touch about 15 questions today. I hope that while you are revising, ensure that what you put in mind that you want to go for non-calculations first. Trust me, they're easy for you to attempt. So I come your way next time, I say, I remain Mr. Femi. Physics under your study path. Bye for now. Thank you. Ẹ jẹ́ má bínú sáà, mo gba time yín.